Hello, everyone, and welcome to the course on complex social systems, modeling agents, learning, and games. Today, we'll have a lecture on complex interactions. It will be given by our famous lecturer, Dr. Lino Antulov-Fantulin. And with this, I'm handing over to Lino.
Thank you, Dirk. Can you confirm that you can see my slides and you can hear me well? And then I continue.
Absolutely.
Okay, and please help me if there are some questions in the chat. Okay, so thanks everyone for joining. At the end of the lecture, we will also briefly discuss how a good project should look like. So we will give you an overview of some of the projects that were done on previous years, and we will share this GitHub repos with you, so you can check them as a reward for participating in a lecture. Okay, so as you recall, last time we were speaking with methods of reinforcement learning, and we were talking about policy gradient methods. What we will be speaking today is what happens when interaction of agents is governed not just about randomness or specific let's say, interactions, but when these interactions are governed by a structure or topology that can be described with networks. Okay. The outline of the lecture is the following. At the introduction, I will say why networks matter, why they matter for modeling agent-based systems. And then I will try to give you the fundamentals of network theory. I will briefly touch upon about modeling global network structure and local network structure. I will talk about some of the tools that you can be using to analyze networks, in particular around different libraries, and also the tool called Gephi. And at the end, because we have had also quite of interest from certain projects, we will also give you just a glimpse of dynamics and spreading phenomena, where the focus will be on epidemic spreading. So why networks matter? You can say that behind complex systems, there are structures, and these structures of interactions, they can be between these components, they can be described with network. So what is a network? So mathematically, we can say that this is a graph, okay, but then why would we have a separate word for it? And why would we call it a complex network? So usually we would say that network and graph are synonyms. So graph from graph theory is defined as set of nodes and set of edges. The synonym of this object is a network. And the reason why we have two names is because two different communities were studying the same objects, and they were usually coming from different perspectives. Some of them were coming from more theoretical side that try to analyze mathematical structures that are and patterns that are emerging in a graph theory, and a different community came from a way to use the tools that can describe better the reality. Okay, but we need to give also the working definition of what a complex network is. I have said what a network is, that it's a synonym for a graph. So a complex network, that is a graph with non-trivial topological properties. Non-trivial meaning that they do not occur in regular graphs or random graphs, but often occur in graphs of real systems. Okay, so when I have said here, I have used also two classes, regular and random graphs. We will try to define them in more details later. So it is also very important to say what this lecture is not about. I will also show you one example of a network that we will analyze. For example, this is a network, and here we are using a tool that's called Gephi. So here we are having a set of nodes that are these circles, and we are having edges that are connecting different nodes. Okay, what this lecture is not about. clearly, it's not possible to provide extensive review and technical details of all the results in the field of complex networks. Although this is a relatively young field, it already has quite rich literature inside. But this lecture will give a broad overview and introduction to complex network interaction among agents in complex systems that are described with complex networks. So let us start with the first picture, why networks matter. And I don't have to do a specific motivation, but I will use a historical one. So this is an art painting from Florence that is essentially describing the Great Plague of Florence. So why networks matter? They matter for epidemic spreadings. Real contact networks of agents are usually a bit more non-homogeneous. Okay, and here I'm only showing you the example of a network that is the high-end sexual escort prostitution. And here you have two types of nodes, one that are referring to male and female. This is the data set that was published, and it's possible to publicly analyze it. It's also a temporal network. And afterwards, when I have showed you some of the examples of the networks, I will also show you where networks also matter. So here, this is the satellite image of USA in August 13, 2003, before and after the famous blackouts. And what you can see in this figure is that on left-hand side and right-hand side, you see that certain parts of a country during a night are in dark. Okay, so this picture or this image somehow tries to motivate for something that's called cascade failures in networks. And they are one of the prototypical examples of the dynamics that can be happening, meaning that when one electricity node is failing due to the overload, it can cascade to its neighbors. And in this kind of a way, we are having certain cascade process. I don't need to motivate anymore that social networks are also one of the examples of networks. Here you are seeing the mapped version of different edges between different users that are embedded based on their origin location. Also, you are aware, for example, that we are having financial networks. We can be talking about a network of Bitcoin. So here in the networks of Bitcoin, we need to define what are the nodes. So the nodes can be, for example, the sets of addresses, so wallets that can send and receive cryptocurrencies. And the edges exist if there was a transaction from one set of wallets to a different set of wallets. There is also a biological networks. Here we are showing the nodes that are denoting different proteins. And you have an edge if they are interacting with each other. So here we would be talking about protein interaction networks. And after all of this, I would just try to directly jump into it and explain from scratch fundamentals of network theory and how we are modeling networks. Okay. So as we have said, a network is a set of nodes interconnected by a set of links. And now one way how you can fully describe this network structure is something that's called adjacency matrix. So at this stage, I would just ask who of you already had a prior familiarity with graph theory? So maybe you can write to chat. Do you know what adjacency matrix is? So that I know how to.
Let's see. Okay, 2, 3. Any more people? I think you can still teach them a bit.
Okay, super. And there is one raised hand. So shall you maybe unmute yourself and directly ask a question? Or it was this raised hand was indicating yes. If it was not indicating yes, then just ask a question. Okay, but let us define. So from our point of mathematics, we can say that we can incorporate the structure of a network into the rectangular matrix. Okay, if we are talking about n components in a system, we are having then this matrix is going to have n, it's going to be dimension of n times n. And if we are talking about very simplified system where only edges can appear or not appear, then we would be placing 1 or zeros inside. Okay, and then you would have a quadratic rectangular matrix A, and then you could use the tools of linear algebra, or for example, from spectral graph theory, to analyze this type of objects. So this is the reason why it's important that we start with a description that already has certain type of mathematical power in it, the machinery that we can use. Of course, there are different descriptions, sometimes in algorithmic examples. Do you see what could be a problem if we are talking about large networks and if we want to represent our network as an adjacency matrix? So can you maybe write if you already can spot what can be an issue? So I'm not seeing anyone, so I will just say, so just to store, there is already one answer from Hector, so I'll read. It could be sparse if they're only, if they're single edges. Only one edge can be stored in an entry. So you are storage problem. So essentially, yes, the storage problems. It means that it would the storage would grow as n squared. But if our someone already pointed, if our graph is sparse, then we would not need to store zeros. So we can alleviate this problem to a certain extent. But if the graph is dense, then storing it is certainly a problem. Okay, so you need to be aware that there is kind of a storage problem. Okay, if we are talking about large graphs. In order to continue further, we need to define what is the degree of a vertex in an undirected network. Is the number of edges that are connected to it. Okay, and we can directly, for example, pick a certain node and then say what would be the degree here. So we would just count the links that are attached to this node. So this node would have degree 1, 2, 3, 4, 5. Okay, very simple. We are also having another definitions that are important. We're talking about directed or undirected graph. So in undirected, you don't have a direction. Are we talking about weighted graph? Are we talking that we are having certain type of cycles? So cycles would mean that we could go from node A to node B and then return back to node A by following directionality or not following them. We also have trees. We also have bipartite graphs. And let us now say, do you maybe know what is the definition of a tree? So if someone can write here, it would be good. And then we would go for definition of bipartite network. So in bipartite graph, we have two types of nodes, and usually you see a lot of these things in, let's say, information retrieval community. Also machine learning recommender systems. For example, you could have documents and entities, and from this matrix, you can actually do the projection. You can do a projection to documents or, for example, to entities. More generally, we would say if we are having type 1 and type 2 nodes, and if A is describing, if A is the incidence matrix that is describing which type 1 node is connected to type 2 nodes, okay? Then in linear algebra, if we write an object that is another matrix that's written A times A transpose or A transpose A, we would be getting projections to type 1 or type 2 nodes. Okay, in this kind of a way, in this projection, we would say are certain two nodes sharing the same opposite side of a node together, then we would have a link between them. Okay, and I will also see that there is a right definition of a tree, a graph with no cycles. Okay, And let us proceed. Okay, so now we want to talk about centrality measures. So centrality measures would somehow tell us how important a node is. So directly from this definition, you would have to understand that what I have said up so far, that this definition is not somehow precise. What does it mean important? Is it important for structure? Is it important for dynamics? And what does it mean that it is important for structure? Okay, so from that perspective, we would have to have certain criteria when we are talking about centrality measures. And we'll start with the very basic one that's called the degree centrality. And it's just the most intuitive measure. And it just captures the most influential nodes with respect to this basic definition. But now I would just like to read the following or define a new measure. And I would like to ask you, can you maybe recognize what this would be? So we say XYZ centrality is based on a simple concept. And this concept would say the following: a vertex is more important if it has more important neighbors. So you are recognizing some kind of a recursive definition. If we denote xi as the importance of node I, then this centrality that we still have not named can be calculated with the following expression. We say xi is sum over k. We have then this adjacency matrix ik, xk. So here we would, this matrix A would tell us to which nodes in our first neighborhood we are connected. And now my question to you is, if we define some kind of a recursive structure or a recursive definition that is defined via this formula, do you see what is this measure? For example, is it related to certain type of problems in mathematics that you have encountered up so far? Okay, so I'm hearing an eigenvector centrality. So, but what is then the problem? Can you specify? The relation is to the problem of eigenvector centrality. Is a good answer. Can you maybe tell me what would be then the problem? The related problem would be naturally, as you have already said, eigenvector problem. Okay. So let us proceed. Yes, this is the eigenvector problem. And here, if you recall from linear algebra, what is the eigenvector problem? You are having some kind of, now you can be looking at it from linear algebra perspective. You're having certain vector x that describes the importances of nodes, and you're having a linear operator that acts on this vector. Okay, then you will get another vector, and this vector would be the same one as an input one. Okay, so this is then very specific eigenvector that is associated to the eigenvalue 1. Okay, so this is directly the description of this problem. Let us then define a few more measures. One is, for example, a centrality. Another centrality measure is called the closeness centrality. For this, we would have to define the notions of shortest paths, the notions of geodesic paths. And let us just briefly say that the geodesic path is the shortest path between two vertices. And let us denote it with dij, okay, as the length of this geodesic path from node I to a vertex j. Okay, now the closeness centrality would be that for certain node you sum the reciprocal version of this shortest path distance to all other nodes, and this then closeness centrality would tell you how close all other nodes are to this node. Okay, there is also an important definition of betweenness. That for which we have to now jump to the pairwise interactions, and we say that sigma st is the number of geodesic paths between pairs of vertices vs and vt, and then this would count the number of geodesic paths that are passing through node vi. Okay, and then the betweenness centrality would be expressed via the following equation, where we are summing across all pairs and normalizing it. Okay, and with respect to these four definitions of betweenness, closeness, eigenvector, and degree centrality, you can actually see that the same network can have different values when we are talking about the importances of nodes. Okay, so for this, I will also show you the tool that's called Gephi. Okay, we will say that, for example, now we want to import certain network. I will export this network for you, and you will have it on Moodle. Let's, for example, import corruption network. Okay. Here we will say that this is undirected graph. Okay. So now we've got the graph inside of this tool. So this tool is, you can think of it, Gephi is like a Photoshop for graphs. So now we would need to, we have imported the network, but we don't have any layout. So what is a layout? Layout would be that we are now assigning certain coordinates to each node.
Nino, I'm
yes?
not sure you have already answered to the question.
Which one?
It should be eigenvalue centrality and betweenness centrality, right?
Yes. I think that I did answer it, but let me confirm one more time. Yes, this is the eigenvector centrality that we were speaking about. That was the one that was connected to the recursive definition of the importance. Okay. So now let us, for example, analyze this network. So in order to analyze this network, we would have to do some kind of layout. Let's assume that this layout is just some kind of an optimization process that is somehow placing the nodes at certain coordinates in R2 space. Okay, so now this is, for example, the network we have obtained. Give me a moment. Unfortunately, now my computer got stuck. Can you still hear me?
Yes, we can hear you.
Yes, I would
see any moving pictures.
Yes.
I mean, your camera is fine; it's working, but
yes, but I cannot anymore move my slides. So
yeah, that's the digital revolution.
yes. So let's make also then 2 minutes or 3 minutes break, and I will have to log off and log in again, and then continue when I unblock the view. Okay.
Yeah, I think that makes sense.
Okay. Maybe we can also answer certain questions students have regarding the projects, and I need to unblock this. Okay, so I'll be back in 2 minutes. Sorry.
All right, so if anybody has a question regarding the presentations, don't hesitate to ask them. I'll stop recording for a second.
Yes, please go ahead.
All the figures of merit that we've seen right now respect to nodes, are there figures of merit for the graph itself that one can look at?
Sorry, I didn't hear the first parts of there are figures regarding the node.
Yes, so we look at the order of the nodes, the centrality of the nodes. But
so you mean, yeah, perfect. So descriptive quantities. Yes, of course, like for example, I think Nino would answer this even better, but for example, you could characterize specific graphs based on the degree distribution of the graph. For example, what Nino mentioned in the beginning, you could have regular graphs, for example, lattices, where you have a grid and each node is connected to exactly 4 nodes around it. These are regular graphs, and you could actually find potential measures that help you understand whether a graph is regular or use a degree distribution as well, and so on. So yes, you could have, if that was the question, you could have actually metrics, let's say, that help you characterize the graph and not only the node.
Mhm, mhm. I guess I'm curious because, like, for example, right now the graphs we are doing are random. So I was wondering, like, what kind of figures of merit of the graph could we look at, change, randomize those figures instead of just the graphs, you know, to monitor how our graph is behaving.
So again, I would highly encourage you to ask me on that question. From my personal experience, for example, if I remember correctly, you could check the Watt-Strogatz graph, and there you could see there are some parameters, for example, link probability and so on, that you could play around with, and then you could generate, for example, denser or sparser graphs only by changing the parameters. And then you could study behavior of your phenomenon, for example, when your graph is sparser or when your graph is denser, if this is what you had in mind.
Thanks. What did you reference? Sorry, what was the reference you talked about?
I will send you a link from Wikipedia. It's the Watt-Strogatz graph.
Okay, thanks.
For example, and yeah, of course, there are like a lot of graph structures that you can parameterize, and then you can see under different parameters what's the behavior of your phenomenon, for example, propagation, etc. Nino is here, so yeah, perhaps you could also repeat the questions for him. And
Yes.
there was,
maybe I could add that many of the randomized graphs are being produced by starting with regular graphs and then having certain rewiring probabilities, and that could be varied from 0 to 1. And depending on that, you know, it would be a more random or less random graph. And many of the dynamical features of the graph would also, I mean, if there's a dynamics on top of the graph, would also depend on those parameters. So we have, for example, just recently done a study in my own team regarding opinion dynamics. And so there are certain kind of network features that determine the dynamics. And that is, of course, the kind of things we're interested in. Back to Nino then.
Yes, thank you. So can you confirm that you can see back my slides?
Yes, oh, good.
Okay, super. So as I was saying, looking at different centrality measures, we would end up with different views around the important. And it is very important to know that they're painting the different picture of what the network or what this structural importance is telling us. So there are different kind of more advanced centrality measures. For example, one is assuming that nodes can have that they can contain information, and that another nodes are having links to those nodes that are having information. And so we can say, for example, that each vertex network have a hub centrality, contains information about the best authorities, and an authority centrality contains useful information. So you can think of it, I know someone who has the information, and this type of relationships. So the authority centrality, the ones that contains information, we can somehow define it as recursively. So recursion is going to be visible at the end, but there's some kind of a sum of all the nodes that are pointing to us from all the hubs, and hubs are the nodes that know who knows the information. So this is the linear combination. Then we can say that again, that the hub centrality of a node is proportional to the sum of the authority centralities. Okay, so in this type of a way, you can also define a centrality that's called hub and authorities, and in matrix notation, they could be written in a following manner. X vector is alpha times A times Y vector is beta times A transpose times 6, and from this you can devise by putting Y inside, you can devise the following equation. And then essentially for this type of centrality measure, you need to calculate essentially singular vectors that are connected to the eigenvalues of the operator A times A transpose or A transpose A. Okay, So this is optional, and for those that want to study more, please look at this Kleinberg paper. Okay. Now, the next question that I would like to ask us, what is the connection to dynamics? So can you tell us, are central nodes more important, for example, for very specific dynamics? That's called epidemic dynamics. So can you a little bit think about it? And let's, for example, talk about degree centrality. What do you think? So am I hearing? Okay, I would assume that you are assuming that you are having some kind of a prior assumption around this. And I'm going just to show you some of the very nice examples. There is one comment from Nicola. Well, I guess it's easier for the epidemic to spread if it's infecting a central node. Okay, thank you. So now check this theoretical example. You are having this synthetic network. You're having node 1 that has, for example, certain type of connection in its first neighborhood. You're having node 2 that has also some kind of a cluster of nodes. And then you're having a node 3 that has the third cluster of nodes, and they are connected via these chains. Okay. Okay. And now what we can do is we can now theoretically calculate, for example, what is the expected value that a certain node will infect nodes, other nodes, and other nodes in this network, and we can calculate this in asymptotics of time. So, for example, we can calculate what I'm talking about. Let's denote a random variable y that is measuring what is the total number of nodes certain node will affect. Okay, so then y1 would tell us what is the number of nodes a node 1 will infect. Y2 would tell us what is the number of nodes a node 2 would infect. Okay. And now, as this is a stochastic process, so for example, if this is a stochastic process, we would have to define what is the process that we are talking about. But let us for now say that we are having certain epidemic spreading, okay? And let us say that with certain probability, you can infect your first neighbor in discrete time, and with certain probability, you can recover, okay? Now, I have now, let's say, fully defined the rules how stochastic process interactions look like. So you're having a transmission and recovery. So for nodes that know more about epidemic process, this would be a discrete type of susceptible infected recover process that we will talk at the end. And now, when we take the expectation, it would tells us what is the expected value that certain node will infect. Okay. And now, what I wanted to show you also in this kind of a graph, what we are changing on x-axis is the probability that node infects one of his neighbors in asymptotics of time. So this goes from 0 to 1. So this is the probability. So this is essentially the effective parameter of this dynamics. So if this p x11 is 1, it means with almost certainly you will infect your one neighbor. And if it's 0.4, it means with 40% you will affect it in asymptotics of time. Okay. And now what happens is that, so x-axis is essentially controlling, it's a control parameter that tells us something around the epidemic process. And now what we see is, as we are changing this control parameter, or we are changing the dynamics, we see that the ranking of nodes is also changing, which is something surprising, which means that in a range from 0 to this value, node, this expectation of a difference is positive. After the expectation of difference is negative, which means that the rankings of node 1 and 2 is changing, okay? So this is kind of it is for sure a synthetic example, but the point was to show you that rankings do not need to be fixed. So even if you're having a centrality measure, if you're changing your epidemic dynamics parameters of your epidemic, their rankings can change, okay? And you can read about this more in this European Physics Journal B. that I was co-authoring in 2013. But it's essentially showing you that we should be careful how we are ranking nodes based on the structural measure, because their role can change when we are considering a dynamics. Okay, so that was the take-home message from the previous picture. Okay, now, if I want to talk about the degree correlations, I want to first ask you, can you spot maybe the difference? If you can, please write it to a chat. So these two networks, they're having a little bit different types of statistical correlations. So if you check, for example, how networks with high degree are connecting to other nodes with certain type of degree structure, then actually you would see that these two left and right hand side networks are quite different. One is we would say assortative. A right hand side would be called a disassortative. What does it mean? I will now define mathematically. So let us now say that we are having a conditional probability if we have a degree k, that we will be connected to some node that has degree k prime. If we now sum over all k primes, we would got the expected value that we would get the average degree of the nearest neighbors of node with degree k. Okay, so this is a function that is now a function of k. And now, based on this property, we can say that in uncorrelated networks, this KNN of k is independent of k. Okay. The correlated network, this is where this correlation is positive, KNN of k, or has a positive, it's larger than 0. We call these networks assortative. And when we have a decreasing function, we call it a disassortative. Okay. And now if you see here, for example, you see that high degree node is connected to a lower degree, high degree node to a lower degree. And here it's maybe harder to spot, but it's assortative, meaning that you are having positive correlations. Okay. What is also very important is to say that usually this type of degree correlations, they are also showing you something around the emergence of organization with respect to different types of systems. Biological networks, technological, tend to have disassortative mixing in general. Social networks are having assortative mixing. Okay, there is something, also one definition that I would like to tell you at this stage. It's called clustering coefficient. Clustering coefficient tells us in our first neighborhood how many nodes are also friends to each other, that are having also connections. Or more formal, we would say out of all possible edges that we could have in our first neighborhood, we want to see how many we really are having. Okay. So the definition of clustering coefficient then is taking number of edges we have in our first neighborhood, divided by total number of possible edges. That is essentially this factor here, that is saying that is connected to the ki over 2. Okay. For example, for node CA, in its first neighborhood, only these two nodes are sharing an edge. So we would just be applying a formula 2 times 1. One node, we are having one edge, dividing it by other possibilities, and this is the clustering coefficient. Node CJ would have actually a 0. Okay. And most of real networks in information social and biological systems are characterized by similar topological properties, like small average part length. So meaning that you can, when you pick two nodes at random, their length is not large. High clustering coefficient, meaning that we are seeing some kind of a closing of triangles in our first neighborhood. We are having a fat tail scale-free degree distribution. It means that our distribution of degrees in a network is not somehow normally distributed, but it has a fat tail, meaning that we could have nodes that are having very few orders of magnitude larger degree than like what is the average one. We would have presence of degree correlation. We would have presence of communities. Okay. And now I'm listing you some of the topological properties of these networks. For example, for the Internet Autonomous Systems, Protein, Metabolic Network, Watership, and Actor Network. So here, for example, you can check the first moment of this network. This is the degree distribution. This is the average shortest path that is also quite low with respect to the size of a network. Okay. Clustering coefficient that is also quite high. Then this is the exponent in degree distribution that is somehow characterizing degree distribution k to the power of minus gamma, where gamma is the exponent. And we are also having whether or not we are talking about assortative or disassortative mixing. Okay. So now let me pose you one, let's say, model network. Let's say that we are having a random network. We are having n vertices, and let's say that probability of edge occurring between two nodes is p. Okay, and now based on this, just based on this information, we're having n vertices, and pairs of edges is connected with probability p. Can you tell me something around the degree distribution of this network? Can you maybe write, do you know how you calculate this degree distribution? Binomial, yeah, but binomial is written here, but can you maybe unmute yourself and try to give maybe a formula for binomial distribution? But from first principles understanding.
Well, we
Yes.
have, let's consider one node, and we
Perfect.
have n-1 other nodes, and for each one of these other nodes, we can have an edge or not. So
Okay.
with probability p, we do have an edge, and with probability 1 minus p, we don't have an edge, and we have to multiply all these probabilities with each other, and which gives us p to the k in this case.
Correct.
Minus p to the n minus k, and well, that's p binomial.
Yes. Okay. Thank you. Thank you for helping me. Yes. So essentially, this is a binomial distribution that essentially looks like something like similar, like Gaussian-like, or it can be approximated with Poissonian also. Under certain constraint, and this type of networks are also called the Erteshrenyi network. Okay. Now the structural properties of this type of networks exhibit something that's called a phase transition, meaning when we are changing certain parameter, this probability of connecting. When this probability of connecting is below certain critical one that we call PC, then the graph almost surely has no components that are greater than logarithm of size of a network, and above the critical component, it has a components of size of n. Okay, so if you check this, how it would look here on a critical, below it, you are having a lot of disconnected components, and afterwards here the emergence of giant connected component starts to emerge, and yes. This is just somehow visualized with respect to critical parameter that's average degree k in binomial network, but this is directly connected to the probability p, because when you are having binomial, the average degree is that you take this number and you multiply it with p. Okay. So you are having certain type of phase transition that in below certain parameter you don't have. Or the giant connected component, largest connected component has like a very small size, and after above this threshold you are having a large giant connected component. Okay, so the next also important model is called a configurational model. So in a previous one you get this non-fat tailed degree distribution. Okay, and now ideally we would want to have a random graph that can have like an arbitrary degree distribution. So how this model works is that first you assign degrees to all the nodes, let's say it ki, okay? Then you cut all the edges, so you are having half edges, okay? And then you would have to try in this network that now has a fixed degree distribution, it can have also a fat tail. You would then try randomly to connect to collect these half edges, and then in this kind of a way you would create an ensemble of possible networks, which are all having the same degree distribution. And this type of a model is called a configurational model. Okay, as during the break, we were also talking about small world network and Vogt-Strogatz model. In this case, we would have some kind of, we would start, so the generative model to generate this type of a network would start from some regular lattice. Physicists would say that here we are having some kind of a periodic boundary conditions. So things are connected. So there is no beginning and end. Every node is connected to, let's say, 4 neighbors, 4 adjacent neighbors. So first 2, third 4. And then with certain probability P, you would start to disconnect nodes and connect them randomly. Okay, and now as this beta probability of rewiring is going arranging, you would be changing also the statistical properties of the network that you are getting. Okay, when this is 1, you would be getting a completely random network. For 0, you would be getting the value that is regular graph, and in between you would be getting something that has a nice properties, meaning that every shortest path would start to decay. So you would have an average shortest path that starts to be quite low, and you would have an average clustering coefficient that is still high. Okay, and this is the class of Vogt-Strogatz models, or also they are called small world networks. Okay. Generating model for this is actually written here, so you can read it later. Okay, one also very important network model that has heavy tail distribution. It's connected to the price model or Barabashi-Albert model. It's some kind of an evolving network. Regarding the exact definitions, what does it mean to scale, whether or not it's a scale free, we will not go into more details, but there is a little bit of controversy like how things are measured. But let's say that to generate this type of graph, we would start with M0 isolated vertices. At each time step, we would be adding new vertices with M edges. Okay. And then the important fact is that the new vertex will create an edge to the existing node with probability that is proportional to its degree. So this is also called preferential attachment. Finally, if you run this, you can analyze more mathematical details in this paper, but you would be getting a distribution that's now not anymore Gaussian-like, but it has a fat tail. Okay. How does this distribution look like? How does this network look like? You can, for example, visualize it here. And at this stage, I would say that ask, are there any questions up so far? And I would also say that this was just the prototypical, very old or school book examples of networks. In modern way, you somehow are having a quite advanced and rich structure inside. I will just mention a few of them. This is optional for the people that are interested into this topic. So let's start with exponential random graphs. So I would recommend this paper. Exponential random graphs are quite used in the social sciences. Because you can have quite a nice statistical machinery, how to generate them with respect to certain type of properties. We can have a hierarchical random graphs. So I would recommend the paper that's called hierarchical structure and the prediction of missing links in networks that was published in Nature. The idea is there that although you have a randomness in graphs, you are having certain type of hierarchy. One more, let's say, machine learning way of modeling graphs is called Kronecker graphs. That was essentially the PhD thesis of Yuri Leskovec that is currently at Stanford. it was published in the Journal of Machine Learning Research. There, the idea is that you start with small type of a matrix that has that is 2 by 2, 3 by 3, and then by applying certain type of operation like Kronecker products, you would be enlarging this matrix that would somehow represent the adjacency matrix of large graph. And this type of generative models can essentially create quite rich phenomenon of networks. And the idea is that you can take a real network and you can try to infer which kind of generators are most likely to generate the observed network. For this, you would have to do some type of inference that's called Markov chain Monte Carlo inference. Then there is a quite rich literature around stochastic block models and reconstructions. I would recommend these 2 papers. Idea there is that now you're still having a random structure, but now you are having certain blocks, and within these blocks, nodes are connected with each other with certain probability, let's say a higher probability than outside of the block. And then the natural question is, if you are seeing a certain type of real network, can you infer this kind of a blocks? Or now we are naturally talking about maybe a communities. We have to define what community. We will define it in one of the next slides. There is also quite rich frameworks of having a multi-layer networks where the graphs can have multiple layers. So you can be thinking of different layers on top of each other. Then the edges can span from one layer to a different layer. Okay. And this is usually the work that is here is described with multi-layer networks. We are also having temporal networks where now the edges are having certain type of temporal structure. You can have certain type of rules or dynamics that is governing how this temporal evolution of edges is happening. So I would also advise for a overview to check this archive paper. And now I would come back from the first topic that we have had, and it was fundamentals of network theory. And then I would just say something around modeling local network structure, global network structure, and also show you some of the examples of the dynamics that can happen on networks. Okay. So now for modeling local network structure, let us think on the following example. Given a snapshot of the network at time t1, we want to infer new interaction among the vertices of existing network at some future time, t2. So this is usually known as link prediction problem. Okay. So can you, for example, try to think and tell me how would you approach this problem? So if you're giving a snapshot of network, how would you try to infer or like predict which kind of links can appear in future? Am I having someone who can maybe propose it?
But that may have changed during the pandemics, right?
That is true. That is true. Dear. Okay. So,
think of a party, so you know.
Okay, so no forming of the links. No
who gets to know whom?
So what would you if you were like in 90s hired as a quantitative person for predicting who will form links within each other, and you're having a quantitative background, let's say from the ETH, and you are giving this type of problem in let's say certain type of industry, what would be your approach, for example, how to attack this problem? Can you, for example, try to propose something? Okay, so I'm having one answer. That's good. See if neighbors have links to some given node. Okay, so
to ask a little bit differently. So how do you make friends?
Yes, that's like a good question. Are we having any volunteer to try to make friends with friends? Okay. Nice. So now we are already enriching the potential repertoire of tools that can answer this question. So we are seeing one comes from structural assumption, see if neighbors have linked to some given node. Then we are having some kind of assumption that comes from, let's say, social theory, make friends with friends. Are we having any more propositions? No. Okay, so let us proceed.
There are certain kind of social networks, of course, that are also proposing to link to certain people, right?
Yes, yes. So one way actually that was already proposed by naturally by our students is the following. Let's have some score function FUV. We map a score to a particular edge and propose the ranked list of the missing edges. Okay, let us denote the set of neighbors of vertex x by n of x. And let us generate some kind of a function that takes the following. It's called Jacquard coefficient, but what it does, it says for an edge UV, to assign a score, you would take set of neighbors from node U, set of neighbors from node V. You would do the intersection of this set, okay? Calculate the overlap, and then normalize it with respect to the union. Okay. And in this kind of a way, you could do it for all the edges, and then do some kind of a ranking, and then also see why this or how it makes use this type of a score function. Okay. There, I will just mention a different one that's called that is maybe coming from an assumption from mathematics. It's like low rank matrix approximation. So you would say that you would take the original matrix A, okay, and then you would try to compress it or like somehow explain it with a lower number of factors, okay. And usually this would be called singular value decomposition, and it would say that some kind of a K rank approximation of our original matrix is a multiplication of these three factors. And then most probably natural question would be how can or why would this kind of a structural assumption make sense, and why it can really predict the links, and with respect to something that has like a social assumption. And here I would say that a lot of things have been done, and for you can also study it in more detail. So I would advise the following paper, Link Prediction in Complex Networks, the paper, and then you would actually see that there is no silver bullet here for solving this type of problem. So essentially every type of method, it's having some type of implicit or explicit assumptions or hidden biases why it is working. Okay. And then after we have tried to answer the question, what happens locally, so within your first neighborhood, we can also ask a question, the third question, structure at the level of groups, okay, meaning communities. Now, we have already mentioned some kind of communities, so let's say what communities are. You're having already an intuitive, you're having intuition what it is, but let us say that it's a community or a cluster or a subgraph is a subgroup is a subgraph whose vertices are connected more cohesively or densely with outside vertices. So inside they're more packly dense than to the outside. Okay, and then there are different type of for sure tools again how to be solving this type of problems. I would mention only a few of them. For example, Girvan-Newman method of community detection that is based on iterative pruning of the edges with the highest betweenness until the network jays into the components. So here you can somehow be talking about the partitioning of a network. Let's say from one network you come to the two partitions. Then we can be talking about spectral graph partitioning, that is again trying to analyze what are the communities and partitions based on the spectral properties of a graph. Okay. And for example, tutorial on spectral clustering is written also on slides. And what I also have to say that this is kind of a big subfield, a lot of results. There is something that's called resolution limits. When you can detect these communities, there is something that's called modularity. There is overlapping communities. So I would just try to give you like an intuition of what, for example, modularity is connected to. Imagine that you are having certain type of partitioning of a graph to a communities, okay? And now you would like to assess how good it is. So you would like to have kind of statistical hypothesis, statistical null model. And usually you can say that you would expect that your result is significant with respect to the model where you would be randomly connecting the nodes. Because if you're doing it randomly, then all possible patterns that are emerging are due to the randomness of this generating process. And then essentially this notion of modularity is trying to devise how far away you are from this null model where you are essentially reshuffling, reconnecting your nodes with this type of randomization. There is a very nice papers around it by Santo Fortunato from 2010, and also there are more recent ones from Tiago Piexoto and Newman, Generalized Community Network, published in Physical Review Letters. And yes, and with this I would close the topic of the structure, the level of groups, and also motivate one applicational point where when we have already somehow talked about communities and partitioning, I would show you one applicational problem. Imagine you're having a network and you want to partition it for some reason. What the reason is, I will tell later, such that, for example, the largest connected component is, for example, the size of this largest connected component is below a certain threshold, okay? So now you can remove edges or you can remove nodes. Depending on this, you're having different type of strategies what you can make. You can, for example, say that you're having an airport network. You would try to minimize, let's say, the epidemic spreading if you are somehow containing the epidemics, although there are kind of a few caveats around this goal. But let's say that you would like to destroy a criminal or corruption network, and you would try to find a certain type of an algorithm or certain type of rule that can do this. Okay, there is a nice commentary paper from Barabash and COSS that was published in Nature around Structure Perfect, that was essentially explaining the problem, and that the problem is an NP-hard problem from computational complexity point of view. Then there were people where PI was Lenka Zdeberova, and they have had a nice paper that is working on cavity methods, and it is doing the problem of network dismantling that I have just described, how to partition, remove certain subset of nodes such that your largest connected component comes below a certain threshold. Recently, we have also in 2018, we have also analyzed this problem, and we have analyzed it from perspective of weights of these actions. How hard is it to do this if you're having certain type of a COSS function? We have named this generalized network dismantling. So at that point, the current assumption was that cost of removing any node in a network is the same. Here is some kind of a research overview of different papers inside. What we try to analyze better is that cost of removing a node in a network is not the same. It can be arbitrary in a negative weights or like a degree or something else. And there are also other papers that have taken the weights into account. And then one of the prototypical examples there was, for example, to take a network, online social network. Then you do the algorithm that was called min-sum. That was a state-of-the-art method. And then you do the dismantling up to certain size. Okay. The size here was 0.8 of the largest connected component. And then we would calculate what was the cost of doing this. And if the cost was, for example, removing a node was proportional to its degree, because we assume that it's some kind of centrality of this node can be described with degree, or you can use other measures. Okay. And then we also checked what happens when you are doing a side percolation, which would mean randomly removing nodes. What happens when you take into account this cost when you are doing the optimization. And here the point was just to show that the methods that were previously designed for one type of dismantling, when you take the dismantling cost into account, something that they were not optimizing directly, then you see that essentially in this regime, they are not performing good. And then, of course, you can also analyze for these three methods, min-sum, GND, generalized network dismantling, and side percolation. If you're partitioning this node, what are the nodes that you are removing? You can be checking the degrees of these nodes. For example, for the red strategy, you can be checking. So you see that there is quite high number of high degree nodes. Then you can check, for example, what happens with the green strategy, that is the random removal of nodes. And then finally, you can also say what happens when you are removing with this optimizational procedure GND that also takes the node weights into account. Then you see that somehow larger nodes are not favorable because they're having a large cost. Okay. And now, after the problem was introduced, I would just like to say how this problem can be attacked from optimizational point of view. So if you want to partition a node to two parts, you can say that separate cluster M and M prime, then you can write the following objective function that would go over all edges. Aij would tell you if they are connected. Wi and wj would say whether if you're removing certain edge, then you're removing both nodes from both sides. And I'm not going to go to too much details. And vi would tell you, so vi would be an indexing which tells you to which cluster you are breaking it, to +1 cluster or -1 cluster. And then vi times vj essentially tells you either you are breaking are both nodes in the same cluster or they're not. Okay, so if they're in the same cluster, here you would get, for example, 1 minus 1 would be 0. If they're in different cluster, here you would get -1. So you have different weights about the cost that you are having, depending whether the nodes are in the same cluster or not in the same cluster. And this type of problem can be connected to something that's called Laplacian partitioning. So you have to use something that's called modified graph Laplacian. And then this is the optimization problem that we are talking about. So you would want to minimize this objective. You're having this quadratic term of a Laplacian. Okay. Graph Laplacian is usually used in graph theory. It is -a plus d, where d is a diagonal matrix of degrees, and x is the solution of your problem where you're partitioning your nodes. So now this is a quadratic matrix. When you multiply with a vector, you get a vector. And when you multiply with this vector, you essentially get a scalar value. So this optimizational problem is telling you what's the cost if you are removing a certain type of nodes. And yes, then you can do some kind of fine tunings and essentially be massaging this problem in order to get more optimized solutions. But the idea is that you can now take cost into account. Either this cost can be some kind of realistic energy, money, or any other measure that is specific to this type of a problem. Okay. What are the tools with which we can analyze networks? There is a Gephi tool that we have, that I have at the beginning opened. I have had now a little bit of problems using it, and the system crashed. But you have already seen how I was moving nodes there. I will send you the link to this tool. You can download it, and also I will send you certain, you will find the materials around certain nodes that you can analyze. There is a graph tool that is an efficient Python model for manipulation of graphs. This one you would use, it's not that intuitive, but it's used for scalability. You have NetworkX, that one is more popular. It's a bit, I would say, easier to use than graph tool, depending from which background you are coming from. And you have iGraph, okay? That's also binding. iGraph can be programmed in R, Python, and C or C++. C++. Okay, with respect to reading, I would recommend 3 books. Networks and Introduction from Newman, Mark Newman. There is a nice online book, Network Science, from Arbet Laszlo Barabashi. There is also a nice book co-authored by Vespignani. It's called Dynamical Processes and Complex Networks. And with these 3 books, you can actually pick and learn more about the topic. And at this stage, I would just try to also close the part where when we were talking about the network interactions. And we would now go to just a small part where I would just try to give you a glimpse of the dynamics that are happening on networks. And at this stage, I would also maybe ask you for stop for a minute and ask you, do you have any questions up so far before we continue?
So did you make friends with Nino's formulas?
Is there anything up to this point that you would like to ask a question about the structure of graphs? I know that in the audience there are people that are doing the dynamics, so I will also mention here something around the epidemics that they are working on the project. So unless there are any questions, then I would proceed. Okay. So I would like to connect for network dynamics. Now, when we have explained the structure of networks, now ideally we would want to allow certain type of dynamics that's happening on it. One natural type of dynamics is, for example, epidemic spreading between people. Okay. And because Thomas during his lecture was already using this type of machinery of differential equations for modeling agents, I would also start with this approach, where I would, for example, start with a model that was published in this paper. It's called Universality in Network Dynamics, Nature Physics. And in this paper, essentially you are having the following system of differential equations. So for every node indexed with I, you say that its derivative of its current state is decomposed to 2 parts. So the first part, this part here, denotes self-interaction, okay? Something that drives the system of a node without any interactions to others. And you're also having a second part that is connected to the interaction with other nodes, okay? So you're essentially summing for all your neighbors, and you are having certain interaction function that takes state of node I and state of node J. And then depending which kind of function we take, we will have different type of dynamics. Okay. With appropriate choices of these functions, L and Q, these ordinary differential equations can model different type of processes. For example, we can model epidemic processes where then the xi, the derivative here, xi would say, for example, what is the probability that certain node is affected. Okay. We can model biochemical dynamics, where xi would say what is the quantity of certain reactant in, for example, kinetic equations. We can be talking about birth-death processes, where we are talking about certain type of xi would say, for example, what is the population size of certain species. Then we can also say that we can be talking about regulatory dynamics, where we have some kind of gene expressions. Okay, so just by changing this type of functions, we can get different type of binary mean field equations. Okay. Now, which type of functions to plug in? There is a nice table where you can actually now a little bit check which kind of functions we can have here that are describing different type of rate equations. Okay, for different type of dynamics. Okay, and I would now just also tell you that they're kind of this is an optional material, but for those that are interested. In a previous one, we were modeling somehow or assuming some kind of a mean field assumption, meaning that nodes states are not correlated. Here we can Gleason introduced a framework where now he is working with different types of motifs. So, for example, also for the binary state dynamics. For example, the state S, so in type, if it's an epidemic spreading, then S would say what is the probability of having a node that has K degree, and out of these K nodes we have M infected nodes, and also what is the probability that we are having a node that has K degree and out of it M nodes are infected, or in certain other state. So essentially now your motive in a previous equations, the motives were only what is happening on a node index with node I. Now we are, for example, moving to the motives that are connected to the degrees and to the first neighborhood of that node. Then you can also write some kind of a closed system. They are a bit more complicated, but they are including these terms SKM, AKM, and then they are having different transition rules. Okay, but this, what is important, that this type of transition rules, okay, they can be changed, and then you can be modeling epidemics, you can be modeling information dynamics, spin systems, majority vote processes, etc. Okay, so again, just by incorporating different factor functional expressions, you can be modeling different type of dynamics. And finally, for the students that want,
I'm sorry to interrupt.
Yes, please.
Can you please explain what K and M is in the previous? Yes, here.
Yes.
Yeah.
Perfect. Okay. So recall here that I didn't went into too much details, but I will just give you a glimpse. So first, what is a state? Okay. So let's talk about the epidemics. So we are having a motive of a node that has K degrees. Okay, K friends. Out of this K, he has M of them that are infected. Okay, and now this FKM would tell us the rate that, for example, with which we could be we would be recovering. Okay. So this is, for example, one explanation. So it is a rate that describes your first neighborhood that has that is indexed with degree K, and out of these K nodes you have M that are in very specific state, and also for R. So, for example, this would be we can say now one can be for transmission and one can be for recovery. Okay, so that is one way how you can think about it. So FKM would tell you the transmission probability that you spread the disease, okay, or you get it, that you get it from your M infected neighbors. That's now multiplied with lambda intensity. And for example, recovery, that is, for example, in this case, just like independent of your neighborhood. So it's just constant mu. Okay.
Okay, thank you.
Okay, thanks for the question. I introduced this as an option material. There is like a very nice MATLAB code that Gleason has provided. So I would encourage you to play a little bit with it. Okay, and yes, then you can be modeling different type of dynamics. Okay, and now I have actually, for the dynamics, I have showed you, how you can model binary state dynamics with mean field approximation. And I have shown you something, how to model it when you are having a little bit more complex motifs. Node with certain degree, and you know what is in its first neighborhood. Okay. And now I would, for example, go with a certain type of dynamics that has three states that we already spoke about. And that's, for example, susceptible, infected, and recovered the dynamics. Okay. So problem formulation would be the following. For a static unweighted graph, estimate the final outcome of the process that is defined in the following way. Beta dt, it is the probability that an infected node transmits the disease to a susceptible neighbor in infinitesimal amount of time, tt. Okay, and gamma dt would be the probability that the infected node recovers in infinitesimal amount of time. Okay, now with these two definitions, essentially these two rates, we can have different types of algorithms how to simulate this, but I'm going to show you one of them that is based on this paper and on this paper. And essentially the idea is that we take a network that is unweighted for certain beta and gamma. We would now map this type of dynamics to some kind of ensemble of weighted graphs. Okay, ensemble means that we would have a large set of large weighted networks, and the weights in these networks would be on edges, for example. Okay, so from undirected graph we create a bunch of weighted graphs, okay, that are having certain type of weights on the edges. And then from this ensemble of weighted graphs, idea is that we can now extract realizations of epidemic spreading. So now you can think of it that we are having different realizations, similar like when you're throwing dices. Okay, you can have different realizations, and in each compartment now on this picture we would have a different weighted graph. And I will just explain how the weights are created. Now you take, for example, certain edge between nodes I and j. Okay. And for this edge that was unweighted, now you create a weight. Which weight do you create? You create, for example, the following weight. You write either, first you generate two random numbers between 0 and 1, x and y. So this is the first random number. This is a second random number. Okay. And then with these two random numbers and beta and gamma, they're the parameters of our spreading process. Okay. That fully defines the epidemic process. Now, for every edge, we calculate the following values. We calculate negative logarithm of this random variable between 0 and 1 divided by beta, and also negative logarithm of this random number between 0 and 1 divided by gamma. And if this is smaller than this, we assign this weight. Okay, now I will explain why. What is this? If you recall in our Monte Carlo lectures that we have had at the beginning, we have had something that was called sampling from a distribution. Now, when we have defined the distribution that works with beta, the distribution has this parameter beta, and it works according to the following definition. Essentially, time that you need to wait that this event happens, if beta is a rate that it happens in infinitesimal amount of time, then this distribution does anyone maybe knows. So if you're having beta, a distribution that something happens in infinitesimal amount of time, what is now the distribution that characterizes the waiting time? Perfect. It's an exponential distribution. Yes. Okay. And the exponential distribution is essentially written. The density is beta times e to the power of minus beta t. Okay, that's the exponential distribution that your colleague has essentially written to chat. Now, from Monte Carlo lecture that we have had, we learned also to sample distributions. Okay, now we can actually sample the exponential distribution. And because we know the cumulative density function of the distribution and its inverse, we can actually calculate the sample of this distribution. And this is the way that we get. Okay, so this would then be interpreted as the amount of time we need to wait such that something is propagated through an edge. And this is the amount of time we need to wait that some node recovers. So if this quantity is smaller than this one, it means that event that someone will transmit something is happening before a node recovers. So then it means that we would write that this is the time that we need to wait on this edge. Vice versa, we would put infinity. Why infinity? The reason is that we want to have certain type of equivalence. We want to now that shortest paths on this weighted graph are, so the shortest paths is written here, the definition, that they are also telling us what is the time that the epidemic can spread from one node to a different node. So essentially this formula here, quantity on the right hand side is purely structural property that tells you what is the shortest path from one node to another one. And here this is a dynamical quantity from epidemic dynamics, and they are saying that these two things are equivalent. Okay, whether it's approximation or exact, I can take your questions, then we can go talk to more details. How you can find shortest paths, there is some algorithm that's called Dijkstra. This describes the complexity for Dijkstra algorithm. And now what is very beautiful is that this type of algorithm allows you to, by just calculating shortest paths, now you can extract the spreading dynamics of epidemics. Okay, it also, in more general way, we are near the end. You can now use not just the exponential distribution, but you can generalize it to arbitrary distributions. Okay. And then you can have a different type of non-Markovian type of spreading dynamics. You can also unify now discrete or continuous time dynamics. So now the only difference, are you sampling a distribution that's discrete or distribution that's continuous? And in this kind of a way, you can essentially unify different type of phase diagrams in epidemic spreading. Okay. There is this nice paper that we have showed how different types of distribution actually can be mapped to some effective parameter. That is an optional thing for you. And before we finish, I would say that you can look at the extensions of this model with these mappings to something that's called, that has also exposed state. Check this paper. Some challenges in monitoring epidemics, it has been accepted in the following journal. Here is the code. And also you can try out, for example, the mapping process and quarantines in this Google Colab, where you can install the libraries, and where I have implemented this algorithm for you that you can play with it. and that you can get different types of trajectories. So this is only optional for people that want to analyze epidemics with this type of mappings. And with this, I would close the lecture. I'm very glad that you have been active. It's like a very large field that I tried somehow to give you a glimpse of the things that are happening. And please, if there are any questions, I can take them. And yes, and I will pause because we are low on time to the Slack some of the GitHubs of the previous groups that that have used that have written the projects in previous years, so that you can have it as a case.
All right, thank you very much, Nino. Are there any questions or comments? If not, we would finish this lecture and we'll see each other next week. Wish you all the best. Bye-bye.